Hi, welcome back. Now, let us enter the second part of heat conduction. Okay, so back to our formula of heat conduction. The rate of heat flow dq over dt is equal to negative Ka dt dx. Okay, so from this formula alone, we can understand that there are three factors that will influence the rate of heat flow. So they are namely K, which is the thermal conductivity, A, cross-sectional area, and dt dx, which is the temperature gradient. So these three factors, this is how they influence the rate of heat flow. Rate of heat flow, dq over dt, is proportional to thermal conductivity. That means if higher thermal conductivity, the higher rate of heat flow. How to understand? For example, let's say I have two different material. We know that thermal conductivity thermal conductivity K differ by material. Different material, different K or different thermal conductivity. So we have two material here, the glass and steel. So they have different thermal conductivity. We know that steel conduct heat faster compared to the glass. So the steel has a higher thermal conductivity because it can conduct heat easily compared to the glass, which is a bad conductor of heat. Okay, so glass has a low thermal conductivity and steel has a high thermal conductivity. So for the glass, low thermal conductivity means it has low rate of heat flow because it's a bad conductor of heat. Glass is a bad conductor of heat. So the rate of heat flow also, you see, there's only one arrow, you see. So that means a bad conductor, the heat flow only a little bit. I can say the heat flow only a little bit or very slow. The heat flow very slow. So low K, low dq over dt. But the steel is a good conductor of heat. So a lot of heat can flow or heat can flow very fast through the steel. So high K, high dq over dt. Okay. So the higher the K, the higher the rate of heat flow. The rate of heat flow is proportional to thermal conductivity. Cross-sectional area. Rate of heat flow also proportional to cross-sectional area. For example, I have two different areas here. I have a small cross-sectional area and a big cross-sectional area. Of course, the bigger the cross-sectional area, like this one, the big cross-sectional area, allow more heat to flow through. Like if small area, less heat can flow through per unit time. But if the cross-sectional area is big, it allow more heat energy to flow through per unit time. So the bigger the area, the bigger rate of heat flow. So rate of heat flow is proportional to the area, cross-sectional area. Yeah. So lastly, about the temperature gradient. Rate of heat flow also proportional to the temperature gradient. Why? Temperature gradient is about the difference in temperature. Yeah, temperature gradient is about the difference in temperature. Like this one you see, the first one, the difference in temperature is only 30 minus 20 is only 10 degrees Celsius. Yeah, I just write like that. Yeah, the difference in temperature here is only 10 degrees Celsius. So when the difference in temperature is very small, 10 degrees Celsius, so also less heat will flow from the high temperature to low temperature. Because the difference in temperature is so small, so less heat is flowing. Less heat is flowing. When the difference in temperature is very small, less heat is flowing. But when the difference in temperature is so big, like 100 to 0, the difference in temperature is 100. 100 minus 0 is 100. You see? When the difference of temperature between the hot end and the cold end, when the difference in temperature is so big, a lot of heat is flowing per unit time. So when the difference in temperature is big, that means the temperature gradient is very big or very steep. The gradient is very steep. Yeah. When the difference in temperature is big, that means it has high temperature gradient. High temperature gradient. That means a lot of heat is flowing from the very hot end to the very cold end. Yeah. A lot of heat is flowing when the difference of temperature is very big. So the higher the temperature gradient, the higher rate of heat flow. So what I can say is, what influences the rate of heat flow? How to maximize the rate of heat flow? I must use a, that means I must use a steel rod, maybe, or copper rod, and big cross-sectional area. Big cross-sectional area. I must use a steel rod. I must have a big cross-sectional area. Big cross-sectional area. When you have a steel rod, that means the K is high. When a big cross-sectional area, and then I have a very big difference in temperature. That means from 100 degrees Celsius to 0 degrees Celsius, the difference in temperature is very big. Yeah, that means the dt over dx is also very big. Then there will be a lot of heat is flowing. Yeah, per unit time. The rate of heat flow also high. Yeah, that means the higher the thermal conductivity, the bigger the cross-sectional area, the bigger the temperature gradient, the bigger the rate of heat flow. You understand? I hope you understand, yeah? Okay. Then we want to talk about the graphs. Okay, we want to talk about the graphs. Okay. Okay, about this one. I hope you understand about this, yeah? The relationship. Now, I want to talk about the graph. Okay. Now, here we have a well-insulated rod. Okay, well-insulated rod. So, this is just a rod, okay, made of only one material. Okay, so this is a rod that is insulated. Insulated, or sometimes we call it insulated, or sometimes we call it well-lac. So well-lac means well-insulated. So there are two ways to say insulation. Yeah, well, you can say either well-insulated or well-lac. Yeah, both of these means there is something that cover the rod so that no heat is lost. So here we have a rod that is well insulated. That means there's no heat loss, no heat coming out from the rod. Yeah, the heat enter at one end, which is A, and then heat is going out from the other end, which is B. So the heat going in, all the heat going in from A will be, all the heat that going in from A will go out from B. So the heat in is the same as heat out. The heat in is the same as heat out. So for this well-insulated rod, when there is no heat loss, it can achieve steady state. What is actually meant by steady state? Steady state, it means the heat going in will be the same as heat going out because no heat loss from the center or along the rod. It can achieve steady state. No heat loss. So what is meant by steady state? Steady state means the rate of heat flow. Let's say I pick the point A. Yeah, this area. This is A, and this area is B. Okay, the rate of heat flow at A is the same. The rate of heat flow at A is the same as the rate of heat flow in B. Okay, I make it this one. Okay, can you see that? Yeah, hope you can see that clearly. Okay, now again, what is meant by steady state? Steady state means the rate of heat flow at A is the same as rate of heat flow at B. Why? Because no heat loss. Okay, no heat loss along the rod. The heat that going in, the heat that passes through the A, or the heat that passes through the A will also pass B. Now we think like that. All the heat that passes A will also pass B. That's why the rate of heat flow at A is the same as rate of heat flow at B. When rate of heat flow at A is the same as rate of heat flow at B, we say this rod can achieve steady state. We can say it means steady state. No heat is lost, yeah, for well-insulated rod. We can imagine this well-insulated rod like a water hose, a good water hose, where there's no water leaking from the center of the water hose. Let's say we have a good condition water hose. The water that going in from one end, okay, all the water that going in from one end will come out from the other end, because no water leaking from the center. So all water going in from this end will also go out from this end. So that means the rate of water flow at the earlier part will be the same as the rate of water flow at the last part. Okay, same. Water in equal to water out. And then, I want you to look at this graph. What is this graph? This is the temperature versus distance graph. Temperature versus distance graph. This graph tells us the changes in temperature along the rod. Changes in temperature along the rod. So, as we learned before, why do the heat conduction happen? Why do heat conduction happen? Heat conduction happen because there are difference in temperature. Difference in temperature. That means they must have a difference in temperature. They must have a high temperature end and a low temperature end. Then only the heat can flow from high temperature to low temperature. If both ends have same temperature, the heat don't flow. You understand that or not? So we have two different temperature. You see that? Then we have two different temperature and then only the heat can flow. And that tells us about this graph. That tells us about this graph. You see, heat flow from high temperature to the low temperature. You see this, the arrow direction? The arrow direction is to the right. What this tells you? The arrow going to the right, the arrow of the heat. This arrow shows the direction of the heat flow. The heat flow from the heat flow to the right. What does this tell you about T2 and T1? The heat flow from T2 to T1. What is this telling you? This tells you that T2 must be the hot temperature or the high temperature. T1 must be the cold temperature or the low temperature. Heat only flow from hot or high temperature to low temperature. It's just like the water flowing from the high pressure point to the low pressure point. The water only flow when there are different in temperature. The water only flow when there are different in pressure. Okay, the water must flow from high pressure to low pressure point. So the heat also flow from high temperature to low temperature point. So this graph tells you the heat flow from T2, which is the high temperature, the heat flow from high temperature to the low temperature. So along the rod, the temperature actually decreases. Why decreases? Because the heat flow in the direction of decreasing temperature. The heat flow, again, the negative sign here means the heat flow in the direction of decreasing temperature. So this graph shows you decreasing temperature. You see that? The heat flow from high temperature hot end to the low temperature cold end. So T2 is the high temperature end and T1 is the cold temperature end. So this graph also gives you the temperature gradient. You see that? The gradient of this graph is the temperature gradient. And all this while we are saying that this temperature gradient is negative. You see that? Because we are using the cold minus hot temperature, we will get the change of temperature negative. That means, what is it means? It means that this dt over dx is always and always negative. dt and dt over dx, this temperature gradient always what? Always negative. You won't get a positive temperature gradient. The temperature gradient is always negative. So this temperature gradient is always negative value. That's why negative multiply negative, you get the dq over dt positive. Okay, dt over dx is negative. Negative multiply negative, you get a dq over dt, which is positive. Yeah, negative multiply negative. Temperature gradient is always negative. So that's why you see this graph, the gradient of this temperature versus distance graph, the gradient of this graph is the temperature gradient. And you can see this gradient is always negative. dt over dx is always negative gradient. Understand that? Okay, enough of that. Now, okay. Now I want to compare the point A and point B. Yeah, this area, this is the same rod. Yeah, still using one rod. Yeah, a single rod using the same material. So the heat flow through A will be equal to heat flow through B. Rate of heat flow through A equal to rate of heat flow through B. Yeah, when achieve the steady state. So I put in the value, the equation negative Ka dt over dx for both. Okay, so from the graph we can see the gradient is the same. Yeah, the gradient is the same. So we can say the K is also the same. Yeah, when this dt over dx is the same, area same, so K also same. K also same. That means the whole rod is only one type of material. Only one type of material. So that's why the K is the same, because you are using the same material for the rod. Yeah, it's only one rod. The K is the same. When the temperature gradient is the same, that means the K is the same. Now, I want to, what if you have two different rods? What if you have two different rods combined? That means two different material. When you have combination of rod, that means you have two different materials, or two different K. Two different K. You have that means you have K1 and K2. Two different. Just now it's only a rod. A rod, that means you're only one material. Only one K all along. Yeah, only one K. Yeah? That means the K is the same. Yeah. So what if you have two different material combined in series? So this is the graph. It looks like. Yeah, it's still insulated. Okay, it's still insulated. Why so important about insulation? Why so important about insulation? When insulated, that means this rod can achieve steady state. What it means by steady state? That means the rate of heat flow is constant all along the rod. Because no heat loss. Okay, so you see this, you have two different material rods, two rods combined in series, and they are both insulated. That means all the heat that enter the rod 1 will come out at rod 2 also. Okay, so that's why I can say these insulated rods can achieve steady state. That means the rate of heat flow dq over dt 1 is equal to rate of heat flow dq over dt 2. That means all the heat passes through the rod 1 will also pass through the rod 2. Yeah, these two, yeah, they are equal. Okay, now, yeah, a lot of explanation. I'm so sorry, but I have to explain this so that you can understand. Okay, so now dq dt, I substitute with the formula negative Ka dt over dx for both. Okay, as we know, these two rods, they are different material. So the K is different. K1 and K2. K1 and K2, they are different. Now, what happened to the temperature gradient? dt over dx. The only thing is similar is the cross-sectional area. Cross-sectional area is the same as I see. They have the same cross-sectional area, but they have different material. They have different material, that's why they have different K, K1 and K2. So how this affect the temperature gradient? You see that? Okay. Now you see, the heat still flow from high temperature to low temperature. Do you see that? So T3 is still the hot temperature. You see the very high temperature. And T1 is the cold temperature. T1 is the cold temperature. And the gradient, you see, the gradient for both graphs is still negative. As I told you, the temperature gradient dt over dx is always negative. Always negative. So you see the graph, the temperature gradient always negative. The gradient, so for this graph, if the question asks you to draw, the graph always have negative gradient. Don't ever draw positive gradient. If you draw positive gradient, if you draw the graph the other way around, which is this direction, then this is wrong. If you get a positive gradient for the temperature versus x graph, this is wrong. The temperature gradient graph always have negative gradient. Because why? Because heat always flow from high temperature to low temperature end. Understand? The gradient must be always negative. Now, back to this graph. Okay. So we have two different rods. They have two different K. So we have K1 and K2. So when they have different K, of course they have different temperature gradient. Okay? For example, okay, if let's say the first rod K1 is a bad conductor, that means it has very low K. Yeah, the first one, the K is very low. Okay, so the K2 is a good conductor. That means it has high K, isn't it? It has high K. So a bad conductor has low K, low thermal conductivity. A good conductor has a very high thermal conductivity. So how it affect the equation? Okay, so when K1 is small, because both sides must be equal, isn't it? Because the rate of heat flow for the dq dt1 must equal to rate of heat flow dq dt2. Because all the heat pass through the rod 1 must also pass through the rod 2. Because it is insulated and no heat loss. All the heat pass through 1 must pass through 2. Because it insulated. Steady state. No heat loss. Okay? Now, okay. So you see here, you have low K here, and both sides must be equal. When you have low K here, the rod 1 has a low thermal conductivity. So the temperature gradient must be higher, must be very high. But for the right hand side, the K is the thermal conductivity is high. So the temperature gradient must be small to balance out the equation. You understand or not? To balance out the equation. This K is low, the dt dx must be high. You cannot be K low, dt dx also low. You cannot be the thermal conductivity low, then the temperature gradient also low. Then both sides become not equal. You understand or not? It cannot be, this side low, K is low, temperature gradient low, equal to K high, temperature gradient high, which is wrong. Okay, these two sides not equal. So when this K is low, when the thermal conductivity of rod 1 is low, the temperature gradient must be high. And if the thermal conductivity is high, the temperature gradient must be low. You see that? So this is what happened to the graph. The first one is a bad conductor. It's a bad conductor. It has low thermal conductivity. So what happened to the gradient? The gradient will become bigger. So smaller k, bigger temperature gradient. So when K1 is small, so what happened to the temperature gradient? The temperature gradient dt, so the dt dx for the first one will be high. So that's why you see the graph is very steep. It has very big gradient. Okay. Now for the second rod, the thermal conductivity is high. So the temperature gradient must be small. So that's why the graph become not steep. The graph become not steep. It become the low gradient. So dt dx for the second rod become low. To balance out the equation. So low K, low thermal conductivity, high gradient. High thermal conductivity, low gradient. This is what happened. Okay? This is what happened. When low K, high thermal conductivity. Okay. So we can say the first part of graph is a bad conductor. The second part of graph is a good conductor. How to understand more about this? Okay. Why a bad conductor has a big gradient? Why a good conductor has a small gradient? Let's talk about concept. Okay. So imagine like a bad conductor. What example you have a bad conductor? Glass. Glass is a bad conductor. Very low K. Okay, glass. We can imagine like this. If we have a cooking, we use wok, isn't it? We use a wok to cook. Okay, so below the wok, heating is 100 degrees Celsius. 100 degrees Celsius. But after so long, the food cannot be cooked. The food is still 20 degrees Celsius. You see the difference in temperature? 120, 100 with and 20 degrees Celsius. The difference is 80. That means the temperature gradient is very high. Yeah, this end is 100. The other end is still 20. You see that the difference in temperature is so big. So this glass is a very low thermal conductivity, but the dt dx is very big. Okay. The lower end is already 100, but at the top is still 20 degrees Celsius because this is a bad conductor. Glass is a bad conductor of heat. So forever it cannot cook the food. Yeah, the temperature gradient is so big. So the glass is a bad conductor of heat. The temperature gradient is so big. 100 with 20. Temperature gradient is so big. It's a bad conductor, low K. That's why it has a that's how it works. So how about the steel wok? Steel wok, it has a very high K because it's a good conductor of heat. This is a good conductor of heat. So imagine it's like if you have steel wok, below is 100 already. Very fast the food is cooked because the temperature gradient is very small. dt over dx is very small. That means in a short while, below is 100. In a short while, the food become 90 degrees Celsius. In a short while. So 90 and 100, the difference is only 10. The temperature gradient is very small. That's why steel is a good conductor. When it is a good conductor, the temperature gradient is very small. So easily the heat can cook the food. Yeah. Okay. So that's about the okay, about this temperature gradient. Yeah. Now that's all about insulated rod. So one thing I want to emphasize about insulated rod is insulated rod or well-legged rod can achieve steady state. That means the rate of heat flow at one end with the other end, the rate of heat flow will be equal. We can use the formula dQdt equal for first part with the second part, the rate of heat flow is constant, no heat loss. What if non-insulated rod? What if non-insulated rod? You see, now I'm using one rod. This one is insulated and this one is not insulated. What if non-insulated rod? Non-insulated rod means their heat loss. But heat loss cannot achieve steady state. So it's like this. Heat in, you see this is not insulated. Not insulated means got heat loss. Okay, so when heat in from the part A, a lot of heat in, but the heat that going out from the other end, which is the B, the heat out is only less, only a little bit, because majority of the heat already lost through the center of the rod. It's just like a leaking water hose. Water in a lot, but along the rod, along the water hose, the water already escaped. A lot of the water already escaped. So the water that going out only a little bit, less, maybe dripping only. Okay, so this non-insulated rod cannot achieve steady state because got heat loss. So the rate of heat flow, this is the important part. The rate of heat flow at part A is more than the rate of heat flow at part B. For non-insulated rod, the rate of heat flow at part A is more than the rate of heat flow at part B. Here, a lot of heat flow. Here, less heat flow. That's why the rate of heat flow at part A is more than part B. So they are not equal. Or just simply write the rate of heat flow at part A at part A not equal to rate of heat flow at part B. Not equal. Okay, so the what happened to the graph? Yeah, the graph become a curve. Still high temperature going to low temperature, like high pressure going to low pressure for the water, but it's a curve. Unlike insulated rod, it's a straight line. But for non-insulated rod, it become a curve. Okay, become a curve because of this. So what if a non-insulated combination of rod? What if you have two rods? Still, the rate of heat flow at rod 1 will be more than the rate of heat flow at rod 2. They cannot achieve steady state because got heat loss. So it is also a curve. Okay, it's also a curve. So also have different gradient. Like this one, I can see. What I can see is this temperature gradient. Okay, right. So this temperature gradient I see is this temperature gradient is smaller. This one is steeper. This temperature gradient is bigger. So what I can summarize here is which one is a good conductor? The smaller gradient is a good conductor. The bigger gradient is a bad conductor. Bigger gradient, low thermal conductivity. A smaller gradient, higher thermal conductivity. A bigger gradient, lower thermal conductivity. Okay, that's it. So to summarize this graph, what I want to say is, well-insulated rod can achieve steady state. That means the rate of heat flow can be equal. Okay, the rate of heat flow can be equal. But for a non-insulated rod, the rate of heat flow is not equal for both sides. Yeah, the rate of heat flow is not equal to both sides. And for an insulated rod, the graph is always straight line. But for a non-insulated rod, the graph is always a curve. It's always a curve. Okay. Yeah, I think that's about it. And always be careful. The temperature versus distance graph, the gradient is always negative. Don't draw a positive gradient. Yeah. Always you begin with high temperature and with low temperature. Yeah. Heat always flow from hot to cold. So you always begin with a highest temperature, ending with the lowest temperature. Yeah. The temperature distance graph always like that. Always begin with high temperature to the low temperature. Okay, that's all about the heat conduction. So the next part is about the thermal expansion. Thank you for watching.